So here's a fun quote. Well, maybe not a fun quote, but a quote about mathematics. The essence of mathematics is not to make simple things complicated, but to make complicated things simple. And Stanley Gooder. Now, a lot of people taking a math class, you might be one of those people, often feel like, that doesn't sound like the mathematicians I know. It doesn't sound like the math I know. It seems like everything's trying to make things complicated. But there's a reason that we are working through these processes. We're working up to be able to solve complicated things systematically. And it's nice to be able to do those things. Our goal in math is to simplify things. The world is complex, and math can help us get a little bit of a better handle on it. Now, what's our goals for today? Last time we talked about matrix multiplication. So I have two matrices, and what does it mean to multiply them together? Now we want to go and say, well, okay, now that you have this idea of multiplying, what can you do? Well, you think about numbers. What's a really cool number to multiply by? 1. You know, like previously, we talked about what's a great number to add? 0. So we have this notion of the zero matrix. And if you add the zero matrix to something, you got what you started with. That's what we call the additive identity. It doesn't change when you add. So you say, well, is there a multiplicative identity? Is there something we can multiply by that doesn't change when we multiply? And we do have such a thing. It's called the identity matrix. It acts like our 1. And it has different sizes depending upon what kind of matrix you want to multiply by. This is just 2 examples. But for our purposes, this will be roughly where we try to stay. You can have it be as big as you want. The other thing we're going to talk about is the inverse of a matrix, almost like division. And so what's the idea? Well, I want to multiply and get 1 out. So, but in this case, our 1 is the identity matrix. So our goal is to say, well, if I have a matrix A, is there some matrix that somehow cancels it out by multiplication? We'll call it A inverse. And I know it's tempting to say, oh, A inverse is like 1 over A. Kind of, but it's a little bit more subtle. But that's not a bad intuition. And there are ways to find it. We have the tools. And that is, you make a really big augmented matrix. Now, previously we've talked about making augmented matrices with 1 extra column. Now we make an augmented matrix with a whole extra matrix. And then we just do our row reduction as before. And if we're able to start with A on the left and the identity on the right, and by row reduction are able to get identity on the left, then it's A inverse on the right. So we'll talk about that and hopefully do some examples. So that's where we're going. All right. Well, start with the identity matrix. So again, as we just mentioned, it's the matrix that acts like 1. So if you take I times A, something you probably see a lot, IA here, you get A. A times I, you get A. And one thing that must be true is that this matrix, it's a square matrix, and the size comes from context. So we don't say, oh, the identity matrix, we can say, well, it's the 2 by 2 identity matrix, the 3 by 3 identity matrix. Oftentimes we just say identity matrix and just say, it's the one that makes it work. Now, we went through it and said, you know, we have this notion of matrix as a linear transform. And I think this helps explain what's going on. And so what is the identity matrix? Well, it's where the input matches the output. So it's the function, if you think about it in terms of functions you're familiar with, it's the function f of x equals x. What you plug in is what comes out. And so when you're doing this extra round of multiplication, essentially it says, oh, if the input matches the output, then the identity basically does nothing. So that's why it just sort of passes through the identity in terms of linear transformations. So let's try examples. Now we can do this the long way or the short way. I don't know if you have a preference, but do you want to do it the long way or the short way? Are you sure? Well, if you were to do this the short way, you'd say, look, what do we have? The identity matrix. Now check the size. What size is our identity matrix? 2 by 2. What size is this matrix it's multiplying by? 2 by 3. 2 rows, 3 columns. Now, you have to check, does it make sense to multiply? Well, the terms, the 2's match. Yes. So, now you say, look, without any work, once you recognize this is an identity matrix, this multiplication makes sense, then you say, I have the identity matrix times something, what's the output going to be? Just a something. So, what's the first row of the output? 1, 3, 5. And the second row? 2, 4, 6. So once you know you're multiplying by the identity, it's that quick. Now you can go through and do it a little bit slower. You can say, okay, first row, first column, 1 plus 0, 1. 3 plus 0, 3. 5 plus 0, 5. 0 plus 2, 2. 0 plus 4, 4. 0 plus 6, 6. So you can do it the long way too. You'll still get the same answer. All right. How about the next one? We have this matrix 1, 3, 5, 4, 6, 2, 1, 7, 9 times 1, 0, 0, 0, 1, 0, 0, 0, 1. Do we know what this is going to be? Well, what do we see? What do we see? We see the identity matrix. Okay. Now the nice thing is it doesn't matter whether we multiply on the left or on the right. Does this multiplication, will it make sense? We have a 3 by 3 times the 3 by 3 identity. Do the 3's match? Well, yeah, because they're 3's. So, the multiplication makes sense. One of them is the identity. So what's the output? It's the matrix on the left. And again, you can go through. You can say, well, 1 plus 0 is 1. Then you can say, okay, 0 plus 3 plus 5. You can do the multiplication. 0 plus 0 plus 5. And if you just do it very patiently, you'll see, lo and behold, you get the matrix. Well, this is just taking advantage of the fact we have the identity matrix. All right. Now the last one, it's not the identity matrix on the left or on the right. Well, we have to throw in a bit of a review. Let's try this out. Let's see if we can remember how to multiply these together. We can multiply these together because a 2 by 2 times a 2 by 2, the insides match. So we get something which makes sense. And the outside tells us that the output will be a 2 by 2. All right. So what do we get? So starting with the first entry in the first row, first column. Minus 5 plus 6, also known as minus 5 plus 6 1. Next, first row, second column. First row in the first matrix, second column in the second one. 1 times 2, and 2 times minus 1. So 2 minus 2. The answer? 0. You might be suspicious. That's all right. I'm a very suspicious character. All right. Second row, first column. So second row, first column. So 3 times negative 5, and 5 times 3. Minus 15 plus 15 gives 0. Last entry. What will it be? What will it be? All right. Second row, second column. Second row in the first, second column in the second. 3 times 2 plus 5 times minus 1. The answer? 1. Like, whoa, we got the identity. So we're saying, well, that's interesting. Here, we have 2 matrices that don't look anything like the identity, but we multiplied them together and we got the identity. And you might say, okay, there should be something about these matrices. If we're thinking of these as functions, which transformation is just another way of saying a function, somehow they're undoing each other. So we want to talk about what's going on. So that brings us to the question about the inverse of a matrix. And the inverse of a matrix says, okay, it's something like division. We're trying to divide out. It's the closest thing to division we'll get with matrices. Before we get very far, we have to add a warning. We cannot always find inverse of matrices. They don't always exist. Just like when we think of numbers, there is one number you can't divide by. Do you recall that number? 0. So there's a number you can't divide by. And if we're thinking of inverses as kind of acting like division, it says, okay, so it makes sense that there's sometimes, must be some situations where inverses don't exist. So first off, what is the inverse of a matrix? Well, we say B is the inverse of A if we multiply A times B, or if we multiply B times A, either one, we get the identity. Now, as a reminder, A times B and B times A do not have to be the same, generically. So the fact that they both are equal to each other and they're equal to the identity gives us something. And we write this matrix B as A to the minus 1, A inverse. Now, what can we say? Well, to have an inverse, you need to be square. That follows from this requirement. If it's not square, this can't work. Because if you think about it, it says, well, the number of rows of A has to equal the number of columns of B. In other words, for this, number of columns of A, I can do this. Columns of A equals rows of B, but also vice versa. Columns of B equals rows of A. But because we get the identity out, identity is a square matrix, and so they must be equal to each other as well. So it forces things to be square. So if you don't have a square matrix, you automatically know that does not have an inverse. End of discussion. You stop there. If you do have a square matrix, maybe you have to work a little bit harder. Okay. So let's take a look. Which of the following has an inverse? We have some matrices here. So 3 matrices, 3 possibilities for things having an inverse. All right. Well, let's start with A. 3, 1, 4, 2, 7, 1. Does A have an inverse? No. Good. Why not? Yeah, it's the wrong size. Not a square matrix, so no inverse. So that was quick. All right, good. Well, looking ahead, we cross our fingers and say, well, maybe this will be really quick if they're all not squares. But unfortunately, the next two are. Okay, so let's get to B. B is the matrix 2, 3, 0, 0. Does B have an inverse? No? But how does that stop us from having an inverse? Well, we have to be careful here, right? Because you can have lots of zeros and still have an inverse. So the fact that it is connected to the fact that you have zeros on the bottom. I do agree with that. So let's think about, suppose there were an inverse. All right, we can imagine such a thing were true. And then, if there were an inverse, let's see. If there were an inverse, I could multiply it by an A, B, C, D, and out would come 1, 0, 0, 1. The question is there any such A, B, C, D? Well, let's try this out. Okay. So, as we carry through this operation, we get 2A plus 3C. All right, I'll just do 2B plus 3D. Then we get 0A plus 0C, also known as 0. 0B plus 0D, also known as 0. And that has to equal 1, 0, 0, 1. Do we see any problems that might say like, uh-oh, that's not looking promising? Anything jump out? Yeah, this 0 in the second row, second column, can't equal that 1. It's not possible. It can't be done. And so we get to this situation where it's like, no inverse. And in this case, the problem really does stem from this row of zeros. If you have a row of zeros, you run into problems. Now, it's not the only problem that you can have, but I just want to illustrate it is a problem. Essentially, what you want to have is like every row should give you something new. If we think about this in terms of equations, we want every equation to somehow give us new information, because a matrix is a collection of these equations. And when we get to a situation where it's like, oh, we're not getting new information, then we're going to get in trouble and we won't be able to succeed. Okay, so far we failed on 2 of them, but we failed for different reasons. One of them was the size, and one of them was essentially like, hey, there's something wrong with your matrix. But now we have C. 3, 2, 4, 3. Does this have an inverse? By next time, we'll be able to look at this and automatically say yay or nay. But we're not next time. We're today. We have to build up to that. It's not so clear. So what do we do? Well, let's try to make one. So here we go. We're going to make an inverse. So we have A, B, C, D. We want this to be 1, 0, 0, 1. So if it has an inverse, this must be true. All right, so we write down, what is this product? Well, we do the multiplication, 3A plus 2C. That is the first entry, first row, first column. 3B plus 2D. 4A plus 3C. 4b plus 3d. And remember, this is supposed to equal 1, 0, 0, 1. Well, that gives us 4 entries. And in order for this to work, every entry has to match. So that leads us to 4 equations. So let's do the first column. 3a plus 2c 3a plus 2c equals 1. 4a plus 3c equals 0. The second column, well, that gives us 3b plus 2d equals 0. And 4b plus 3d equals 1. The reason I specified columns is when you look in the first column, you just see A and C. When you look at the second column, you just see B and D. So we actually are a little bit better off than 4 equations with 4 unknowns. We have 2 collections of 2 equations and 2 unknowns. So we just have to solve these equations, and life is good. All right, do you want to start with the AC group or the BD group? AC. All right, we can do a couple of different things. We can do elimination, we can do substitution. Any preference? Should we do some substitution? We haven't done that in a while. It's not so bad to practice that. Notice the second equation, we can solve for, let's solve for A. So we can say 4a is minus 3c. So that says A is minus 3 4c. Now, what can we do? Well, we can take that and plug it up into the first equation. So we get 3 times negative 3 4c plus 2c equals 1. Or minus 9 4c and 2 can be written as 8 4c equals 1. Or, if we add, that becomes minus 1 4th c equals 1, which tells us, what about c? Tells us c is negative 4. If c is negative 4, a is negative 3 fourths times negative 4, so a is positive 3. All right, that's those 2 equations. And this is the problem so nice, we get to do things twice. All right, I'll use the first equation and solve for d. Why not? We get 2d is negative 3b. D is negative 3 halves b. And now we can plug that into the other equation. We can say, all right, 4b plus 3 times negative 3 halves b equals 1. Sorry, it's getting a little cramped there. But 4 is 8 halves b minus 9 halves b equals 1. Or minus 1 half b equals 1. So what is b? Minus 1 half times b equals 1. B is minus 2. What is d? Well, put negative 3 halves times minus 2. Out comes 3. So, here's the candidate. We have A is 3, B is negative 2, C is negative 4, and D is positive 3. Now, I say candidate, we actually are done. Once you know that you have a square matrix, and you say, I found something so that if I multiply the 2 together, I get the identity. Now, it doesn't matter whether it's the, A times A inverse or A inverse times A, the other order will automatically work. So this is the answer for sure. But just to be careful, I just want to point out we've only verified multiplying on the right works. I just want to show you that, hey, if we had multiplied on the left, that will also work. We don't need to rederive it, we just need to check it. But I will say this is a step you don't need to do. It will always work, as long as you start with square matrices. Well, what do we get? 9 minus 8, that is 1. 6 minus 6 is 0. Minus 12 plus 12 is 0. Minus 8 plus 9 is 1. All right, so that is indeed the answer. 3 minus 2 minus 4, 3. Okay. Well, all right. So that seems tedious. We'd like it to be faster, especially if we had to go and solve a 3 by 3 matrix. That would take us a lot of time if we tried to do that method every single time for finding the inverse. So we're going to get better at it. And to help us get better, we want to understand what's happening with the inverse. What is going on? So we talked about, think of the matrix as a linear transform. So it's a function. You put numbers in, you get numbers out. So A, you put in some collection of numbers, and we tend to represent that as a special matrix. It's called a column matrix. Some people call it a vector. So just think of it as there's a single column. And now you put that in, the machine runs, out comes an answer. Y1, Y2. Well, what the inverse is trying to say is, hey, instead of running the machine forwards, run the machine backwards. So you want to sort of undo it. In other words, if you put the y1, y2 in, out comes the x1, x2 that you would have started with. So we're running things backwards. That's what the inverse wants to do. Now we've seen this with functions, right? We have like the functions, we've talked about e to the x, and then we have log of x. Or you have x cubed, the inverse x to the 1/3. So it's the same philosophy. We want to have the inverse as being the machine running backwards. Now you might say, great, but have we done that before? And the answer is yes. We've been doing it a lot. It's almost the only thing we have been doing in some sense. Now to understand why, think about what this represents. So A, it's a matrix. It's your A, B, C, D. Right? We're just representing it as a matrix. Now, when we talk about linear transform, what we're saying is we're going to take a linear combination of the inputs. So that looks like A x1 plus B x2, C x1 plus D x2, and these become your outputs. Now, if you think about what we've been doing is we've been starting with these equations where we tell you the numbers over here and ask you what are x1, x2. That means we've been telling you the output. We've been asking you for the input. So we've been doing this sort of inverse problem for now the past 2 weeks. So we're like, hey, we've gotten good at that. So let's do that. All right. Oh, it's already in there. Good. So now how do we take advantage of it? Well, if I want to make the inverse matrix, I want to say I want the whole matrix. Well, what I can do is I can say, if I know how to grab a column, then if I can just grab every single column, I can grab the whole thing. So here's idea number 1. There's certain special vectors, our column matrices, which grab a single column. So I claim that if we do this multiplication, something nice comes out. So I have E, F, G, H times 1, 0. This does make sense as matrix multiplication. It's 2 by 2, 2 by 1. So we're going to get out a column again. What comes out? What's the output of this multiplication? Carry out the multiplication. What do you get? So we have E, F, G, H times 1, 0. What comes out? E, G. And so let's do this one then. E, F, G, H times 0, 1. What comes out? F, H. This isn't a coincidence. What ends up happening is when you multiply by a vector, you're just grabbing combinations of the columns. This says grab one copy of the first column and no copies of the second column. So you're grabbing one copy of the first column. This says grab no copies of the first column and one copy of the second column. And so then what comes out is the second column. So if we could solve the inverse problem for these special, sort of easy to identify vectors, what we really would be finding is we would be finding the columns of the inverse. Once we have that, we can piece the whole thing together. That's sort of big idea number one to help us do that. Now there's a second big idea, which says we have been doing the augmented matrix method to help us solve one problem at a time. But it turns out you can use the augmented matrix method to solve multiple problems simultaneously. So in other words, we don't have to do two problems. We can do one big one. We can combine it together. Why does this work? And what do I mean by that? Well, suppose I want to look at the question, I want to find x and y, so 3x plus 2y equals 4, and 4x plus 3y equals 1. But I'd also like to know an x and y so that 3x plus 2y equals 5 and 4x plus 3y equals negative 3. Now, we've known how to solve these problems using augmented matrices, which says, well, look, if I just saw the first problem, I would think of the augmented matrix where I take the coefficients 3, 2, 4, 3, and I have this 4, 1 on the right-hand side. If I just saw the second problem, and here I wish I had smaller fingers, I'll try my smallest finger I have available to me, then I would say, I'd put the 3, 2, 4, 3 on the left and the 5, negative 3 on the right. Now, the claim is I could do both of them at the same time. So I put the first problem, put that column in, and the second problem, put that one in. The key is that the left-hand sides are matching. Now, why does it work? Well, when we think about what happens, we do row reduction, and row reduction is fixed on this part. We look at the left-hand side. So regardless of what the right-hand side is, that's always along for the ride. And it's always the same process that you do on the left. The right hand just follows along. So I can do both simultaneously. 2 for the price of 1, for all intents and purposes. So we put these two ideas together. That of, if I could just find the inverses of special columns that look like 1, 0 or 0, 1, and saying, hey, I could do both of those at the same time. That gives us our procedure. So here we go. If you want to find the inverse, you say, I'm given a square matrix. If they give us a square matrix, we say, no inverse, stop, can't be done. But you say, okay, we're given a square matrix. Now we're going to set up the augmented matrix. On the left, A. On the right, I. Now, why I? Think about what we're trying to do. We're trying to grab the columns, and so that's where you see the 1, 0, 0, 1. That's I, if you put those two together. If you have 3 by 3, it's the same idea, 1, 0, 0, 0, 1, 0, 0, 0, 1. So we're trying to figure out the columns of the inverse. So if we solve, this will give us the columns of the inverse in order, but having the columns of the inverse is the inverse. So we set up our augmented matrix. We carry out row operations to put this into reduced form. And if the reduced form looks like the identity on the left and some matrix on the right, that matrix on the right, that's the inverse. If we can't get I on the left, so we end up with like a bunch of zeros, it's just like you cannot get I on the left. The matrix does not have an inverse. So that's the procedure. And once you understand, it's not too surprising. And the nice thing is it's relatively efficient. All right, so let's use our procedure. So we're asked to find the inverse of some matrices. 2 minus 3, 4, 5. 2 minus 3, 4 minus 6. Which one do you want to start with? We get to do it twice. All right. We'll start with the left. All right, good. Yes. Okay, so starting with the left one, we're going to set up 2 minus 3, 4, 5. So put the matrix on the left. Identity 1, 0, 0, 1 on the right. Now, your mindset is you're doing row operations. You focus on the left-hand side. You want to put it into reduced form. Reduced form is trying to make it look like the identity matrix. So it's the same thing we've done before. Don't worry about the right-hand side. It comes along for the ride. It will fix itself. So, with the mindset of trying to make things into reduced form, we start by saying the first thing is we'd really like to have a 1 in the 1, 1 entry. It's not a 1. Not yet. What can we do to make it a 1? Scale by a half. Okay, so 1/2 row 1 becomes the new row 1. And we're doing it to the entire row. So we get 1 minus 3/2, 1/2, 0. The second row hasn't changed. That's okay. Now we have the 1 where we want. We say, yes, but we want that entry to be a 0. How do we make that into a 0? What's the procedure to knock things out? What's our elimination rule? So the rule to make zeros is you add multiples of one row to another. In particular, we're going to use the first row. So what do I need to multiply the first row by to make and add it to the second row to get a 0? -4. So you don't have to worry about the rest of it. It's just saying, hey, I've got a 1. I need to multiply by something and add to that to make that entry a 0. So we're going to take -4 times row 1 plus row 2 That becomes our new row 2. So the first row stays as is. Negative 4 plus 4, 0. Negative 4 times negative 3 halves, 6. Plus 5, 11. Negative 4 times 1 half, negative 2. Add to 0, negative 2. Negative 2 times 0 is 0. Add it to 1, we get 1. All right. Now, first column, looking pretty good. That's a pretty good looking first column. But the joy continues. Because now, we get to work on the second column. All right. Okay. These numbers are not the nicest numbers. Well, sometimes that's just the way it goes. All right. We want to make that entry a 1. It's currently an 11. What do we do? What do we do? How do we scale an entry to make a 1? Yeah, just multiply it by the reciprocal. So we're only changing row 2. So 1 over 11 times row 2 becomes our new row 2. That's the row operation that we're going to do. So the first row is unaffected. The second row, multiply everything by 1/11. So that's 0, 1, minus 2 over 11, 1 over 11. We're so close. So close. 3 out of our 4 entries look good, but 1 entry remains. The negative 3 halves. What can we do? What can we do? Yeah, it's the same idea we did here. We multiply the second row by something so that when we add it to the first, we get cancellation. So we're going to take 3 halves times row 2 plus row 1 becomes our new row 1. So the row 2 stays as is. The row 1, well, 0 plus 1 stays 1. That's we take advantage of the 0 here. So we're not going to hurt the first column. That's good. 3 halves plus negative 3 halves makes 0. Nice. And then we just have to be patient here. We have 3 halves times negative 2/11. What is 3 halves times negative 2/11? Well, 3 halves times negative 2/11. Then we're going to add 1 half. Well, we can get the 2's to cancel. So this is really negative 3 over 11 plus 1 over 2. Common denominator would be 22. So minus 6 over 22 plus 5 over 22. Sorry, 11 over 22. Ha ha ha. I got ahead of myself. Which gives us 5 over 22. So there's a 5 over 22. All right. Then we take 3 halves times 1/11, which is 3 over 22. We add that to 0. What do we get? 3 over 22. Now what do we do? What do we do? What do we have on the left? Yeah, the identity. I is there on the left. So according to the procedure, what's on the right? The inverse. So we can come to the conclusion that 2 negative 3, 4, 5 inverse is 5 over 22, 3 over 22, minus 2 over 11, 1 over 11. Probably wouldn't have guessed that right away. All right. Well, any questions on that one? We have a few minutes left, and there was a second one to work on. 2, negative 3, 4, negative 6. All right, so let's go through the process. We think, well, it could be an inverse. Hopefully, we'll get faster at finding it. 1, 0, 0, 0, 1. 1, 0, 0, 1. All right. Again, just do it systematically. If you see something elegant, you can be elegant, but otherwise just think systematically. We'll multiply by a half, just like we did before. So half row 1 becomes row 1. 1 minus 3 halves, 1 half, 0. Leave row 2 as is. Next, we want to knock out the 4. So we'll do the same thing that we did before to knock out the 4. We're going to take minus 4 row 1 and add that to row 2 to make the new row 2, which leaves row 1 as is. Minus 4 plus 4 gives 0 by design. By design. Minus 4 times minus 3 halves. Do we know what that is? 6. Add to negative 6 gives 0. Now we can keep going. Minus 4 times a half is minus 2 and 1. But at this point, what do you see? You see a row of zeros. When you see a row of zeros on the left, you can stop. Because no matter what you do, you cannot put a 1 back in. If you were trying to make an identity, you somehow have to get one of the entries to be a 1. There's no way to recover. So what does this tell us? 2, negative 3, 4, negative 6 does not have an inverse. And the other thing we should add, we can stop if we see a row of zeros on the left. Stop if a row of zeros on the left. All right, we will practice more next time, and that'll be it for today.